and welcome Math 212 students. We are covering chapter 6.4 today, and we're going to look at slope and patterns of change, so I'm pretty excited about that. Here's our topics. So let's jump right into it, and let's look at some graphs here. All right, we have some descriptions of these graphs. Now I want you to notice that we have distance versus time. So let's look at what's going on with each of these graphs, and then we'll try to see which one we can match them up with. So we're covering an amount of distance, and it is a steady amount of distance. So this is going at a steady rate or steady speed because we are covering distance. Notice here in this section, so this is covering this section right here, we are not covering any distance at all. So we're sitting still, kind of catching our breath. The slope of this line is much greater than the slope of this line, and it's still constant. It's still like increasing in distance over a period of time, but I'm covering more distance in a shorter amount of time. So this means I'm going faster here than I was here. And I am, if we were to say that this was our distance from home, I would say that I am far away from home on this one. On this graph, I am covering a distance at a steady speed, going kind of slow though. Then I speed up and I'm still covering more distance, going a little faster. And here I am really zipping along. I'm going really fast right there. So this would be a slow speed, covering distance, but it's taking me a longer amount of time. And you can imagine the values for distance being on this side over here. Now let's look at this graph. We can see that I'm covering distance at a steady speed, but pretty fast. It's the fastest right here. Slow down a little bit. So I'll just say slower. And here I am going the slowest. So let's see which of these. First off, I'm starting slowly. So one of these two will be Alex. So we'll call this graph 1, 2, and 3. The biggest difference in these two graphs is that right here I am stopped. So let's see if Alex stops. Alex starts slowly, so she doesn't stop, so it cannot be number 1. Let's see, starts slowly, goes faster, and then even faster. Oh, Alex, you are number 2. Manuel started quickly, he starts fast, then he goes slower and then slower. Ah, you're number 3. And Rajib starts quickly, then he stops to tie his shoe, and then yes, you're number 1. All right, so it's kind of fun making little stories out of these graphs. So one of your homework, or several of your homework problems, are to interpret graphs. A couple of them you're going to make some stories for graphs. So it is going to be entirely dependent on what you put on your axis. So right here I would put time on all of them. So I'm going to do that for you because time will be on this independent axis. Now you'll notice I went and snipped a couple of graphs and I copied the same one. So on this one I'm going to put distance. And on this one I'm going to put speed. And I'm going to see what the difference is. I'm going to do that for both sets of these graphs. So right here I am covering 0 distance. If this is my home, I am not leaving home. I am not covering any distance over this period of time. From here on, I cover distance at a steady rate. So I am traveling at a constant speed, if you will. So if I was sitting at home, all of a sudden I could instantaneously start going 3 miles an hour or 5 miles an hour because I just started walking. I'm covering distance at a steady rate. Let's see what the difference is here with speed. Now, there's no difference right here because on this, I am traveling 0 miles an hour. But let's put some markers on here and note what's going on here. If this is 5, 10, 15, and 20, we'll call this miles per hour. Notice that I'm not covering distance at a steady rate here. This is speed. I am increasing my speed. From here to here, I'm now going 5 miles an hour. Now I'm going 10 miles an hour. Now I'm going 15 miles an hour. Now I'm going 20 miles an hour. So I'm going faster and faster and faster. So I am increasing my speed. Here was a steady speed over here, so I was not increasing my speed over there. Here I'm increasing my speed. It is as if I have my foot on the accelerator. Okay, so let's look at this. I'm going to do the same thing and look at distance and time, so let me write that on there. All right, let's take a look at these graphs. Pen went away. Oops. Get back on there, pen. Okay. So, I'm looking at this graph. I'm covering distance at a steady rate. So this is a constant speed or a steady speed. And I'm covering distance in miles, and I've covered 5 miles, 10 miles, 15 miles here. Now what's going on at this point is I'm now going back towards, if this were my home, I'm now going back towards home so that I am, looks like I'm about 7 miles away from home, going back towards home at a steady rate, and now I'm going further away from home at a steady rate. All of these things with a steady rate or constant velocity or speed. Let's look at this one over here. This one, what I'm doing is I'm increasing my speed again. So this one would look like increasing my speed. Basically, if I were to look at this graph in terms of distance, let's call this distance, it means I am covering distance faster and faster. Now, I am decreasing my speed here, so I'm decreasing my speed there, going slower and slower, and now I'm increasing my speed again, so that looks like this. So if I were to look at what's going on with my distance, I would see that I'm really covering more distance, because the faster I go, this is faster, whoops, the faster I go, the more distance that I cover. All right, let's look at our next set of graphs. So this is another speed and time investigation. Notice that I'm increasing my speed, increasing my speed, increasing my speed. So if this were 5, 10, 15, increasing my speed, I got my foot on the accelerator. I'm going faster, faster, faster as I go this way. And all of a sudden I've let my foot off the accelerator, and now I'm decreasing in speed until I'm stopped. And this is a 0 mile per hour, if we let this be mile per hour. And so this means I am stopped if I am going 0 miles an hour. If I were to continue this line, this would just mean that I was going backwards. So now I am increasing my speed very rapidly. Not at a steady rate, but I'm increasing. Now look at how I kind of don't increase quite as quickly as I was. And now I kind of stop increasing my speed. Oops. And I just carry on, just go the same amount for just a second. And then I start slowing down. So I let my foot off the accelerator rather quickly, and you might even say I was putting on the brakes here, because I'm slowing down pretty quickly here until I'm stopped again. This one, I'm increasing my speed very quickly. I'm increasing my speed even faster, 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 faster. Let's look at this one. This would be like I had my cruise control on. So let's say that this were 55 miles an hour because we're not going too fast. So this would be like the cruise control is on. And then this is increasing my speed. I want to go a little faster because I want to go 65. So this is going faster. And then this is back to setting the cruise again. Notice that if this were a distance graph instead of a speed graph, distance graph would mean that right here I'm not covering any distance. However, if you're on a speed graph, you are covering distance. Your cruise control is on. Notice distance doesn't change. Distance changes, and here you're stopped again. Your distance isn't changing. All right, so let's see what we have next. All right, well, they don't give us a graph to choose. That's not really nice, but we will draw our own. Whoa! Never mind about that. All right, let's put our pen back here. So, here we go. We're going to have a graph. They tell us to draw a graph, but you know what? They don't tell us, do we draw a distance graph or a speed graph? And it does make a difference, doesn't it? So let's put time here. Let's draw a distance graph. And if I draw a speed graph, it would look different. But we're going to draw distance. They're a little easier. A runner is running at a steady rate. So I'm covering distance at a steady rate. And then we come to a hill, which causes her to run at a slower rate. Okay, still covering distance, but my slope isn't as steep. Once she reaches the top of the hill, she runs down the hill very fast until she reaches the bottom of the hill. So this means we're going to cover distance because we're not running back towards home. Get off there. But we're going to go very fast. And then once we reach the bottom of the hill, we go back to the original pace. We're going to say this is the original, right? So I need to make that slope the same. So let's see if it looks like that. Come over here and do like that. There we go. There's a distance graph, but we don't know if they wanted speed or distance, but it doesn't matter. Well, it does matter. We just have to make sure we describe which one it is. Slope may be interpreted in different ways. Yep, it's the rate of change. Okay. Slope is also the steepness of the line. Yep, we were looking at that too. And we may want to use the words slope and steepness in describing graphs to our students. That way they can start beginning to get this concept of slope. It is, if you've taken a calculus class, you know that calculus is all about slope and how slope changes. That's what it's about. Slope is probably the biggest thing that we talk about in mathematics. So having them have a great foundation in slope is fabulous. How steep is the highway? All right, 17% means that what's going on, if I have a graph, is that's its slope. So it rise 17% means 17 over 100. So it rises 17, we might say feet or whatever, rises I better put this 17 in, it rises 17 feet for every run of 100 feet is what that would mean. Oh, we just described it, okay. If its sign said 12%, how would that be different? That means it would only rise 12 for every run of 100, and it would be slightly less steep than 17%. Oh, we already did C as well. Okay, let's go on to the next one. All right, we're going to look at some patterns. Patterns are always fun to look at. So let's see what we've got. And we've been doing this in our previous section. So we're looking at our nth figure. Start here. If n is 1, I have 1 dot. If n is 2, I have 5 dots. If n is 3, 5, and then 4 more, 9. N is 4, I have what I had for 3 and then 4 more dots, so that's 13. Notice that every time it's add a 4. We describe this as an arithmetic sequence, and if I would like to know how to get that general formula, what's the nth one, I know it's going to be 4 times some n. So let's look at what happened. I have 4 times n because it increases by 4. That's the slope every time. But I started off with 1. So if n is 1, I need a 1 dot. So I need a 1 dot. So I am going to subtract off 3 is what I think it's going to be. Now this is my guess, so I'm going to check it. If n is 2, 4 times 2 is 8, minus 3 is indeed 5. I'm good. Try another one just to check and make sure. 4 times 3 is 12, minus 3 is 9. Yeah, buddy, I got that sucker. So let's go on to the next one. Yes, we looked at slope, or we looked at that change and what was going on from one to another. So we're going to look at patterns of change for some different sequences. And if you had college algebra, this was one of the things that you did in college algebra. These kinds of patterns are on all kinds of different exams that elementary school students have to take. Looking at patterns of numbers is definitely on IQ tests, those sorts of things. So let's look at what's going on. 2 to 5, 5 to 8, 8 to 11, looking what's going on to get from one number to the next number. Looks like it's an add 3 every time. So it's going to be 3 times n, and I need to get to 2, so it's minus 1, I think. So let's try it. If n is 1, 3 times 1 is 3, minus 1 is 2. If n is 2, 3 times 2 is 6, minus 1 is 5, and yep, we got that one. Let's look at what's going on here to get from one to the other. This isn't just a straight up add. This is a times 2, times 2, times 2, times 2. So what's going on here is everything is increasing by some power of 2. So what I'm going to write is 2 to the, and I'm going to write n minus 1. And then 3 is going to be my beginning number. I did that because if n is 1, 2 raised to the 1 minus 1, 2 to the 0 is 1. So for n equal to 1, I have 3 times 2 to the 0, which is 3 times, but I don't mean to write that 2 times, oops, let's do this again. It would be 3 times 1, which is 3. If n is 2, jumping ahead of myself, 3 times 2, 2 minus 1, that's a 1. So that would be a 6. If n is 3, 3 times 2, 3 minus 1 is 2. 3 times 4 is 12. N is 4. And if you remember back from your college algebra days, this is your beginning number, so I knew to write him first. And these are my powers and how it's changing. And it's either going to be, depending on if you call n to be 0 or 1, it's either going to be 3 times 2 to the n or 3 times 2 to the n minus 1. And that all depends on, are you starting with n equal 1 or n equals 0? And they actually do both ways, so you'll just have to kind of check it and see what it is that each problem is looking for. Let's see what's going on here. Now this is adding 5. This is adding 10. This one is adding 20. This one is adding 40. So this is increasing at a pretty significant rate, a little bit different than my others. All right, so this looks like I see 5 times, and we'll just say 5 times 1, 5 times 2, 5 times 4, 5 times 8, just looking at each of these numbers here. And it looks like I'm doing those and then taking away 1 each time to get each of those numbers, just finding my patterns. So I would say that this one is 5. These are all powers of 2, so I say times 2 to the, and I want a 1, so I'm going to do n minus 1, because 2 to the 0 is 1. This is 2 to the first. So if I start with n equal 1, let's do that. N equal 1. I'm going to have, oops, and I need to subtract off 1. 5 times 2 to the 1, put a 1 here, is to 0, minus 1. That would equal 4. Good. N equal 2. 5 times 2 to the 2 minus 1 is 1. 10 minus 1, that's a 9. All right, I think this bad boy works out. If n is 3, 3 minus 1 is 2 squared minus 1. Okay. Oh, yeah, because they're just minus the 1. All right, that looks beautiful as well. Let's see what we have next. Talking about an arithmetic sequence, and what they tell me is that we are going to find our difference in our two numbers, and our difference here was 3, and they tell you that it is your A, and A is your beginning number. And they say if you recognize that it is, an arithmetic sequence, you can just write down that it is A. Our beginning number is A2. 2 plus n minus 1 times d, which is our difference. So let's do the algebra of this. 2 plus 3n minus 3. Adding like terms, we get 3n minus 1. And let's check back a couple of slides, and oh, there it was, just one side. That is what we got. Nice. So we can use this general form once we find our A and our D. That'll get you that n. If you recognize it to be an arithmetic sequence, which means that you add or subtract the same number. Now, as long as it's going up, your D is positive. If the numbers go down, your D is negative. Same thing here. A is your beginning number, so for my A, that's a 3. R is your ratio. That's what you're multiplying by to get to the next one. So for this one, my R was 2. So I'm going to go over here, and I'm going to say A is 3 times R, which is 2 to the n minus 1, which is what we got, I do believe. Yep, there we are. And that's all. All right, that's awesome. I hope you guys learned something with this. And if you have any questions, you be sure and email me. That's rweaver10@alaska.edu, and I'll be glad to help you with any of these problems. Thank you and good night.